The scalar product of two vectors is our next topic. So the product of two numbers a and b only has one interpretation, a times b. So this is what we've seen in numbers already. So similar to like when we were doing vector algebra, we always want to show that our rules, so this rule here, we want to show that it works for vectors. Now, unfortunately, it doesn't work for vectors. We've got multiple types of vector multiplication. So the two types we're going to look at, our first one we're going to look at in this section is the scalar product or dot product. And this is the scalar product of two vectors results in a scalar answer and has notation a dot b. So we say that's a dot b. It can be found for 2D and 3D vectors. Vector product, we're going to do that later. So let's highlight that with a different color, vector product. So we'll do that a bit later. That has... So the vector product, which is these are both forms of vector multiplication of two products, results in a vector answer and has notation a cross b. We also call this one the vector product the cross product and this one the dot product. It is only used for 3D vectors. So now we're going to go to the definition, scalar product. The scalar product of two vectors is also known as the dot product. If we have this vector a1, a2, a3, vector a with its components a1, a2, a3, and b is b1, b2, b3. I've missed. So I'm trying to keep remembering to change notation to what our SACE notation expects of us. So this one, b1, b2. The scalar product or dot product of a and b is defined as a dot b, and we add the corresponding element. So a1 we add to, we multiply with, I'll start again. We multiply each corresponding element and then we add them all together. So A1 times B1 plus A2 plus B2 plus A3, B3. We'll do these in a sec, but this is going to give us a constant answer. It's just going to give us a number. So scalar multiplication, this is a note important here. We've already done scalar multiplication. It is not the scalar product. So scalar multiplication was when we had a vector, we might be calculating a vector A, and it equals k, a scalar, times a vector. And this actually gives us a vector answer. Scalar product is where we do this dot product and we get an answer that's a scalar. So this gives us a scalar answer, and then vector product is a cross b, and it gives us a vector c, which is a vector. So we've got these different products, these different algebraic properties of the scalar product. So these properties can actually help us simplify different equations once we get some vector equations. So I would add these. I'm going to actually write this in navy for you. So add to vector algebra notes, because we've now got some new rules we can use here. Okay, so you've pretty much got, order doesn't matter here. This one comes up all the time. This one is vital. So if we have the dot product of the same vector, it is the same as the modulus of that vector, or the length squared, which when you think about, I'll just write this out here, this is pretty much saying that the square root of a1 squared plus a2 squared plus a3 squared, all squared, this is just going to give us a1 squared plus a2 squared plus a3 squared. So super handy, that one there. These are like distributions. So if we have if we're adding b and c together and then doing the dot product of those, we could do them individually. Okay, and this answer is just going to be a constant. You've also got this here is like our FOIL expansion in algebra. We've got a times c, a times d, b times c, b times d, and these are all dot products. So this is if we add two vectors and we take the dot product of two other vectors added together. All right, we've got one example in this section. So if a equals -1, 2, and 4, and b equals 3, 1, and 2, find the dot product. So the dot product here, I'm going to actually write it out in the notation we should be trying to use, which is -1, 2, and 4. -1, 2, and 4. Okay, and then we've got here 3, 1, and 2. 3, 1, and 2. This means I'm going to add the corresponding element, multiply the corresponding element. So I'm going to do -1, times 3 plus 2 times 1 plus 4 times 2. Okay, and this is going to equal negative 3 plus 2 plus 8, which equals positive 7. All right, that's it for this section. Hopefully a nice quick one for you.